We're going to start right now. For those who are late, just unlucky. But basically, we're gonna go over intro to AI. Um, Last week we went over the machine learning stuff, so this week's gonna be artificial intelligence. But really quick, this is our schedule. It's quite dwindling down. This is March 30th. That's today. Next week is spring break, so obviously we have no meeting. And the week after that, the 13th, is gonna be our last meeting. All right, so without further ado, we're gonna get right into it. We're gonna quickly review what we went over last week, so that'll be really quick. But most important part on this side is machine learning and AI. The big difference is that machine learning is basically algorithms that can learn from data, and AI is software that can solve problems by itself. And then quick machine learning terminology that we went over last week or 2 weeks ago. A label, that's the trait that we want to predict. A feature are input variables. So if we're trying to make a spam filter for email, a feature might be the words in the email text. And obviously, the more advanced the project is, the more features it's going to have. And the simpler it is, the less features it's going to have. Then we have examples. So we have two different types, labeled examples. Those are features and labels. Basically, if I mark an email explicitly as spam or not spam, it has been marked by me. So it's a labeled example. An unlabeled example is the opposite. So an email is in your inbox and it has not been labeled by me yet. So I have not said, is this spam or not? And so it's unlabeled. And we want the machine or the model to train and to predict the label on these unlabeled examples. And then lastly, we have the model, that's the algorithm, and it defines the relationship between the features and labels. And in the two phases, there are training and inference. Training is when you create the model, and you create the model by training and letting the model learn on labeled examples. And an inference is like in when you're applying it and like ready to go production. And so that's when you are applying the trained model to unlabeled examples. So it's like when you're actually trying to use it. And then really quickly, before we get into the AI stuff, we're going to introduce the Chrome offline Dino. So, because we're going to be using that example today. So if you go to Chrome colon / Dino, you can view the Dino game. I'm sure like all of you, or at least 99% of you guys have seen this before, right? Normally it's when like your internet goes out and you're out of Wi-Fi, so this game shows up because you can't access Wi-Fi, the internet. And basically, we're going to be using this example later. So really quickly, if you haven't played this game before, right, your goal is to get a high score. You don't want to die, so you want to jump over your cactuses, and you can jump, duck, and you can run forward, right? And you die once you hit a cactus, and your score is up here. And that's basically all you need to know on how the game works. And so now we're gonna continue. All right, so we're gonna talk about some artificial intelligence terms, and we're talking about these terms again because it's not easy for us to like dive right in and start like coding all of this up because one, you guys probably wouldn't be able to follow along as well. So what we're first trying to do is like make sure you guys can understand it, and we explain how all of this stuff works a bit before we show the demos and show how it actually works like real time. So and this is also like one of the easiest ways to like get a true grasp and understanding of what AI is and how it works. This is obviously a simplified like environment, but we're gonna start anyways. So with agent / environment, that's first. So whenever we refer to agent, we're referring to as the Dino or the AI. The agent's normally the main character. So in our game, the main character or who we control, that's the little dino, right? So whenever you say I want to create an AI to do this, that AI is also your agent. And then we have actuators / actions. Those are like game actions, right? We talked about like a couple of seconds ago. There are three options. You can either run forward, you can either jump, or you can either duck. Those are your three options. And games with less options, like this Dino game only has three options. It's easier to create an AI for, right? Because your AI does not have to like attempt a billion different things at once. It only has to try like three different things. And then lastly, the environment. That's the game, right? So whenever we say the environment, we're talking about like the surroundings. That's the game, right? And so how this loop works is you have your agent. Your agent picks some actuators or actions, right? And these actuators and actions get inputted into the environment, right? So I press the space bar, I tell my Dino to jump. The environment updates, right? I jump over the cactus, whatever, it updates, and it sends me back some sensors. And the sensors are the distance to the cactus, the height slash width of the cactus, the bird height, the speed, and the bias. We'll get to the bias later. We'll explain what that is. But for these four, those are like kind of self-explanatory. And obviously, you can have any types of sensors you want. It doesn't have to be these four. It could be a bunch of different ones. It could just be random sensors. But these sensors are basically like you can think of them as like features or input variables that our AI, our agent, is going to be training and learning based off. So that's our agent and environment. And now we're going to talk about the learning loop. So first off, the learning loop is a loop. So the first step in a loop is it resets the environment. What that means is when I click play, right? I click play, I reset the environment, it starts working again. Then my agent picks an action. The action's either one of three, right? Running, jumping, and ducking. After I pick an action, I return the reward. We'll talk about the reward in a second. I return the game status. The game status is true or false, right? If the game is over or not. So if the dino died or not, right? If the dino died, obviously game status is false, right? If the dino didn't die, game status would be like true. And then it returns the next state of the environment. For us, the next state of the environment, you can think about it as the next frame. The AI takes in frame by frame, right? So the next state would simply be the next frame. And then the AI remembers this reward that we'll talk about later with experience replay. So just think about it as the AI has the ability to remember stuff and remember its past consequences and games. And the AI can go back into its memory or batch of experiences, its past games basically, to learn based off those experiences. And obviously the AI wants to learn off the good games, and we'll talk about all of that stuff later. And so this is the learning loop. If I'm going too fast, let me know. And then reinforcement learning. This is a pretty big concept and it's pretty important. So this is the reward system that I was just talking about. Basically, your agent gets positive points. It gets plus points for doing something good. So if it achieves a high score, it survives for a long time, we'll give it plus points. It gets negative points for doing something bad. So for example, if your agent dies or achieves a low score, we subtract points or we give it negative points, right? And obviously, the more points the agent gets, the happier it is, the better it is. And so it wants to get as many points as possible. And the AI learns from this reward system and correlates certain actions to points. And we do this too. Uh, right? So, how did we learn to walk? How did we learn to speak? All of this stuff. If you think about it, right? If you're trying to train a dog to learn a trick, after it does something correctly, you want to give it like a treat, right? A reward, right? You're giving it a positive point. In society, most of the time, we try to do positive reinforcement, right? If someone does something good, you give them like a benefit, right? You give them plus points, right? There are negative reinforcements too. It's not as common and it does work well also, but it's a bit like immoral in real life. But because we're dealing with like, fake dino AIs, we can give them negative points and they won't feel that bad. And then the bias slash variance, that was the thing we were talking about from the first slide down here. That's the randomness that affects the agent's decisions. So it's like a trade-off. Basically, you can think about it as like a variable between like 0 to 1 that the human that we decide, right? So we can decide what the variable is, and then the stronger the variable is, right? The higher it is, the more it is towards 1, the more random your agent is going to be. And the smaller it is, the more closer it is to 0, the less random it's going to be. And so there are benefits, right? So if you imagine your agent, it's like super random. The bias is like all the way up to 1. That means that each time it's going to be doing a bunch of different things. It's going to be doing really random stuff. And it might take a long time to actually learn because it's trying all this random stuff. On the other hand, if it's too small and it's like a 0, then your agent's not going to try enough random stuff. So it's just going to be stuck doing like nothing, like just running forward the whole time. And it's going to be too afraid to try random stuff. So you wanted to have it like somewhere in between, at a good value. And you can tweak it, we can tweak it ourselves and see, like the different results we get. But that's the bias. And then the genetic algorithm. So this is basically natural selection. I'm not sure if you guys have learned natural selection yet. Hmm. I think that's in ninth grade. Do any of you guys know natural selection? Okay, well, basically, uh, it's this theory by this guy named Darwin, but basically it says that, for example, if you have a bunch of like animals and they were like in the desert, and you can't survive in the desert easily, right? Because you need water, it's too hot, and etc. Basically, all of the species are gonna die off except for those that adapt to like burrow underground or find water, etc. And that's gonna keep on happening generation over generation until you're left with a group of like species, like a smaller group of those species who have adapted to their environment well and can survive. And that's basically natural selection. And we're going to be doing that, um, but with dinos. So we're going to have like multiple dinos working at once. So for example, we might have like hundreds of dinos all trying the game at once, and those who do well and survive, they are the ones who reproduce and create more dinos. I should also mention, by natural selection, like the animals that do survive, they reproduce, and their generations below them hold on and like have some of the traits from the generation above them. So that's why they get smarter over time. And this is the same concept. The smarter dinos reproduce, and their babies, right? Their baby dinos, like gain some of the traits from the generations above. They retain some of the features, but with some variance. The variance was the thing we just talked about, right? With some variance, some randomness, and that's basically how we're going to improve our AI. So you can think about it working as if you have 100 dinos doing the same thing. About 99 of them like die off immediately because they don't know what they're doing. One of them by luck starts jumping over cactuses, and then that one reproduces with other dinos, and their next generations, right, generation 2, generation 3, they start learning to jump over cactuses, but they also have some variance. They also have some bias, right? So maybe one of the dinos with enough variance, they learn to, hey, I should duck under the birds, right? And then after ducking under birds, and they survive more, and so they start reproducing, and they create more generations that learn how to duck under birds as well as jump over cactuses. And that's ideally what we want. And last thing, we have the fitness value. This is optional, so I'm going to speed through it. If you don't understand it, it's fine. But basically, it's how good the solution is. Dinos with a very high fitness value have a higher probability of being selected for reproduction. Um, and how to calculate fitness value? For now, you can just think about it as the dino's score. So whatever score they have is kind of their fitness value. You might be questioning like what the difference between the fitness value and the reward system is, but we're not going to get into that because there's no point. And so last thing we're going to talk about is neural networks. This is also probably a common term that you've heard of somewhere at least. This is based off a real brain. So our brains have a bunch of neurons and stuff. Um, Instead of neurons, think of neurons as like nodes. That's what we want to refer them to as, like a node. Um, but if you don't know what a node is, just think of them as points, right? So we have a bunch of points, and we have a bunch of layers. So the first layer, that's our input layer, and the input layer simply are the sensors from the environments. So these are sensors. These are going to be input layer, and then and then the next layer are going to be hidden layers. So you can have multiple hidden layers, and we're not going to talk about the hidden layers yet. And then after the hidden layers, you have an output layer. And the output layer has the three actions, right? So run, jump, and duck. So ideally, what's going to happen is you get the sensor from the environment, and you do something with the hidden layers, and then all of a sudden in your output, it tells you which out action you want to do, whether it's run, jump, or duck. And each of these nodes holds a weight from 0 to 1. And the greater the number is, right, the closer it is to 1, the more it is present, right? So if like, the speed of the game is very intense, or like the height of this character is very tall or something, your input layer, that node might be higher to 1. And then if you should be jumping over the next cactus, right? If you have a cactus in front of you and you should be jumping over it, then your output layer, the jump should be closer to 1, and the run and duck should be closer to 0, right? And then connections, which are these like connections, right, from input to hidden. These are arrows, right? They also have weights and biases. We won't talk about those yet. And this in total is just lots of linear algebra and matrices, but we won't talk about that either. A good example of how neural networks works is that if you imagine that you are coaching a little league team, and you guys have just won a big game, and you want to ask your team, if they want to go out for pizza or burgers, and then the kids start screaming their preferences, and you go with whatever was loudest, right? Because that's like the majority, and that's basically how neural net works, except it's on multiple levels. So these top level nodes, or the input layer, they get some sort of property, and they scream at different layers, right? The more intense the property, the louder they scream, these input layers. And then you have, so for example, right, we're gonna have a bunch of input layers screaming like it's dark, it's red, it's round, blah blah blah, right? And that's various volumes. And then the next level, the hidden layer, they listen based off these input layers, and they start forming more complex features. So they start, the hidden layer starts screaming, it has a face, it has fur, until finally they scream, right, at the output layer, it's a cat, right? And something like that. It goes from very simple to more complex features to the output layer. And we don't really know what the hidden layers are. That's the importance of AI. The AI decides what the hidden layers are by itself. And that's why it's like so cool and scary sometimes. And that's the magic part, right? All of this stuff is based on feedback. If, for example, this first week your team went for burgers and everyone got sick, the next week they might not be screaming for burgers as loudly, right? And then your neural network is going to update based on that. They're going to be like, oh shoot, I got sick last time. I don't want to scream burgers as loudly this time because it's incorrect. And that's the same concept, except instead of getting sick, think about it as us giving the dino negative points, right? Like our negative points, that's a bad reward. The dino does not want to do that. And that's how the neural net gets trained, and that's how it like kind of evolves. If you have any questions about this, you can let me know right now. Otherwise, I'm going to stop sharing, and Senka is going to show the rest of the demo.
So you want to play the video first?
Oh yeah. You need me to play it?
Oh yeah, my screen sharing is kind of black.
Yeah, no problem. Okay, sorry. Let me share with sound this time. Can you guys hear this?
Hey, so today I'll be talking about how I built the dinosaur game AI and how you can do the same. Now, unlike a lot of other people's approaches where they've either rebuilt the game from scratch or hacked with the source code to make it compatible with their AI, this game is as true to the real game as possible by actually capturing screenshots of the real game and learning from that. Furthermore, the coolest part of this AI is that it's only around 200 lines of code. So let's get started. So this AI is actually built on the principles of reinforcement learning, which, as the name suggests, is a form of AI learning where the AI learns from rewards given by the game. In this game, I had a very simple reward function. If the AI dies, it gets a -10 reward, and if it lives, it gets a +1 reward. This AI was designed around something called Q-learning, where the AI actually learns to estimate the expected reward of doing each action. So in this case, we have 3 actions: jump, duck, or do nothing. And if the AI in this situation decides to jump, it might learn that the expected reward is +1, while the expected reward of going straight, or the no action, would be -10. Traditionally, Q-learning is actually done in a tabular manner, where each state and action, that means position in the game and potential action, is mapped to the expected Q value in a tabular table-like sense. This tabular learning happens with this learning algorithm. However, this method of tabular learning does not really carry over well to a Chrome Dinosaur game because we're dealing with images here, and each image has billions of potential values, and therefore our Q-learning table would be too long. Instead, what we can do is actually borrow techniques from machine learning, such as neural nets and deep learning, to actually train our AI to estimate the expected value for each position. This is done using something called a convolutional neural net, or CNN. As the name suggests, function approximation is just an approximation of the various Q values. So therefore, it's not technically as accurate as doing a tabular sense, but in this case, it's the most practical way of the Chrome AI actually learning. However, function approximation does give us an advantage of being able to abstractify the AI's learning to be used in other cases. Now let's move on to the actual AI implementation. The AI is actually divided into three broad categories: the agent, the environment, and the learning loop. The agent is the actual AI that controls the dinosaur and is responsible for choosing what actions to take and also learning from those actions based on the reward it gets. The agent is fed its inputs or its images from the environment. The environment will actually stack 4 consecutive frames or images together to allow the agent to learn the speed of the game, since the game does speed up as it progresses. The environment is also responsible for providing the agent a reward signal and letting the agent know when the game is over. Now, traditionally, an environment is the game itself, but in this case, since we're using the Chrome AI game that's already built in, our environment simply needs to control that. So in this case, our environment is actually responsible for taking the screenshots, packaging them up into layers of 4 images, and also determining, based on pixel values, when the game has ended and appropriately giving a reward signal based on that. The environment also did a bit of pre-processing on the images in this case by reducing the image's resolution, converting it to black and white, and also making it a bit more contrasty to make it easier for the agent to learn on. And lastly, we have the actual learning loop. This is where the magic happens. This is where the AI actually plays the game and learns from its experiences. The loop is fairly straightforward, and no matter what reinforcement learning architecture you use, this loop is going to stay pretty much the same. The loop starts by resetting the environment. From here, the agent picks an action to take, the environment executes the action and returns the appropriate reward, whether the game is done, and also the next state that the AI has ended up in. The AI will actually remember the reward in the next state based on the original state action pair using something called the experience replay. You can think of the experience replay like the memory of the AI. Now, once the game is finished, the AI can actually go back to its experience replay, randomly select a couple of experiences, and learn based on those experiences. And that's it for this video. That was a fairly high-level overview of how Q-learning, function approximation, and reinforcement learning works. Now I have all my code for this AI posted on GitHub with much more detailed annotations, and you can always leave your questions down in the comments. Thanks for watching, and here's some more AI gameplay.
It'll take me a few moments. Okay, so for our demo, we're just going to show a example for 3 examples of how to implement it in real life. The first one is a non-AI solution of the Dinobot problem. As you can see in the actual source code, we basically simulate key presses like key down, key up. So and the code executes these key presses on an interval. So if the obstacle is like at a certain distance, it will jump at it will simulate a key press event, and that's basically it. If you want to see that, we can. Not sure if that actually opened in the right browser. Probably not, but okay, yeah. So here we have a minified version for this. Go to Dino, and let's paste this into the console if it works. Ah, too close. As you can see, this kind of works, but it's not very well, it's not as good as an actual artificial intelligence or machine learning version. So we're gonna check other examples. So here we have a genetic algorithm implementation for the Dinobot. Uh, yeah. So we're gonna ignore all the other JavaScript code that makes this possible. We're just going to look at the key algorithm. In this case, we have a key algorithm that includes new population, this select reject function, and then a mutate function and a find best function. So the general idea is you randomly create a population and then you simulate you you let all the Dinobots or the you let all the Dinobots in the population play the game, and then you find the best you find the best performing agent in the population, and then you have it become better by mutating it randomly, and that's how it's kind of like natural selection. You have every organism have mutations throughout their life, and that makes them evolve. So this is similar to the biological process. So we're going to see in practice by as you can see at the start, it probably just created a random population that, and it's likely that none of them know what they're doing. So, and most of them get quickly eliminated, and only the one that seems just happens to know what they're doing survive. But after a while, when the speed picks up, well, actually, let us speed this up a little bit. Yeah. So as you can see, it hasn't learned how to like escape the bird. So this is our this is what the last agent's brain looked like, or so in this case, the brain is the model, or like the let's say it's not actually, but it's not. Let's say these are just the weights. So a so a line with a more intense color signifies like how much the decision is based on that node. So uh, yeah, and after each let's say after each iteration of new population, these just gets randomly mutated, and after a while, these will just happen to go into the right. It will just happen to bump into the right configuration for it to perform optimally. So yeah. So right now the target score is 1,000, and well, the high score is only 400 something. So I happen to have a completed version, or like I happen to have a instance of this tab that has reached the high score. So I think uh, As you can see, yeah, here we have a perfectly evolved Dino. It's capable of, basically uh, perfecting the game. It has reached the score of 6,000. So yeah, that's genetic algorithm for you. But we also have a even more advanced solution of the Dino game, which uses well, which I but we have a more advanced version which takes a screenshot, put it in a CNN, and then emulate a actual reinforcement learning agent, which is going to the Python Jupyter notebook. So it looks like the code here is kind of complicated, and we're just going to skim over it. Here are all the modules that's imported. So we have the game class, but this just gives the programmer a way to like access and control the game. And we have the agent. Okay, here we have the screenshots, the functions related to screenshots. Here we have some configuration for the training process. But yeah, here is a convolutional neural network. So we have to actually compute these convolutional networks. And then at the end, we'll have the like fully connected neural network. So output should give us the action. Yeah, this is the entire training process. What the observe is the parameter we use during training, like in the end where we train. That is not part of the that is not part of Keras or TensorFlow. That's just what the author of this code has defined. So yeah, it's pretty complicated. But yeah, I don't. I think this will be the end of the demo for today because this is. I think it has the save data, but I don't have time to cover it today. Yeah. Do you have anything else to cover?
No, I think we're good. If anyone has questions, we'll stay on for a couple more minutes. Otherwise, free to leave. We'll see you guys after spring break, and we'll end the meeting in a couple minutes. Um, Yeah. And we always have the lesson code and all of the links. They'll be on the GitHub, and we'll send it out um, on Google Classroom and Remind also. But that'll be updated like in a couple hours after the meeting's over.
But I know it's kind of cheating, but well, some machines it's already cheating.
Why does it jump so high?
But if you jump any lower, it's gonna hit the cactus. So also, like humans cannot see the cactus like approaching,
Mm-hmm.
but the bot can.
Mm-hmm.
So that's why it's cheating.
Mm-hmm. Oh yeah, the reason why a lot of people like they hard code the game in or they create a game from scratch is because it's easier to like control the sensors and stuff. It's like the dino can see the cactus even though it's off the screen. Um, if you're like using the real screenshot method, you wouldn't be able to like do that really. So that's why a lot of this stuff is like hard coded and etc. I'm not getting any more questions, so we'll wait like another minute, but um we'll end the meeting soon. All right. I'm think we're good to end. All right. See you guys. If you guys do have questions and you're typing it, I'm sorry.